Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 3, and today we're talking about Section 3.3, which is on using the mean and standard deviation together. So the standard deviation is a common measure of consistency in business applications such as quality control. It measures the amount of variability around the mean. Now, the standard deviation is affected by the scale of the data. So what tends to happen is that a sample with a larger mean will tend to have a larger standard deviation. So the example I like, surprise, surprise, exam scores. So suppose that for whatever reason, one of my classes takes an exam that's out of 50 points, and another class takes an exam that's out of 200 points. So first of all, hopefully it's pretty clear that the means in those two classes are hopefully going to be pretty different. So the mean in one class might be 40 out of 50, and in the other class it might be 162 out of 200. So those means are very different. The standard deviation is also going to be measured in points on the exam, and in one class it's going to be points out of 50. And in the other class, it's going to be points out of 200. So I would bet that the class that took the 200-point exam is going to have a larger standard deviation. So what we can do to level the playing field is to use something called the coefficient of variation. So what the coefficient of variation does is it measures the standard deviation as a percentage of the mean. So in the class taking the 50-point exam, if the mean was 40 points and the standard deviation was 8 points, I could say that the coefficient of variation for that class is 20%, because 8 out of 40 is 20%. And so that will, like I said, level the playing field between the two classes, even though one of them has a larger mean. The coefficient of variation will still give me the best idea of which class had more variation. All right, so here's the formula. As I said, the coefficient of variation is just the standard deviation as a percentage of the mean. So this is how you do that, depending on whether you're looking at a sample or a population. If you're doing a sample, it's S divided by X bar. So that's going to give you the proportion. And then when you multiply it by 100, it will change it to a percentage. And for a population, it's the exact same thing, just different notation, right? So with a population, we use sigma for the standard deviation, and we use mu for the population mean. So here's an example. We're comparing stock prices for Nike and stock prices for Google. So if the average price last year for Nike was $59.67 with a standard deviation of $6.64, then the coefficient of variation for Nike would be 664 divided by 59.67, and then multiply that by 100 to make it a percentage. So the coefficient of variation for Nike is 11.14%. And then for Google, the average stock price last year was $1,045.85. The standard deviation was $68.70. $68.70 as a percentage of $1,045.85 is only 6.56%. So although Google had the larger variation, right, $68.70 versus only $6.64, it still had the more consistent price because its standard deviation is smaller as a percentage of its mean. All right, then we have the Z-score. This is very important. We're going to be using these a lot for the next couple months at least. The Z-score identifies the number of standard deviations a particular value is from the mean of its distribution. the number of standard deviations. Note that a z-score has no units. The z-score is 0 for values equal to the mean, positive for values above the mean, and negative for values below the mean. So when I say the number of standard deviations from the mean, a value with a z-score of 1, positive 1, would be 1 standard deviation above the mean. So for example, if the mean was 20 and the standard deviation was 3, a score of 23 would be 1 standard deviation above the mean. So 20 plus 3. And then if you went plus 3 again, you get to 26. 26 would be 2 standard deviations above the mean. That would have a z-score of 2. So we're going to do some official examples here in a second. A data value that has a z-score above positive 3 or below negative 3 is categorized as an outlier. It has a value far from the mean. So those values are pretty unusual. You don't too often see z-scores that are above positive 3 or below negative 3. So here's how you calculate z-score. The formula for the population z-score is z equals x minus mu, and then divide that difference by sigma. So x is the data value of interest, mu is the population mean, sigma is the population standard deviation, and then it's basically the same exact thing for a sample. Just use x bar instead of mu, use s instead of sigma. All right, so here's an example of finding the z-score. What we have here is a list of how many calories are in different fast food hamburgers. And they want us to find the z-score for the Burger King Triple Whopper with cheese. And then they want us to interpret that. So notice that the Triple Whopper with cheese has 1,230 calories. The mean for this sample is 788.4 calories. The same standard deviation for this sample is 359.5 calories. So the question is, how far is 1,230 from the sample mean of 788.4 expressed in number of standard deviations? So that means z-score. So we're going to use this formula. 1,230 minus 788.4, and then divide that difference by 359.5, you get 1.23. So that means the Triple Whopper with cheese is slightly more than 1 standard deviation above the sample mean. It's about 1 1/4 standard deviations above the sample mean. All right, so here are a couple of different things that you can do that sort of relate to z-scores. First, we have the empirical rule, which says if a distribution follows a bell-shaped symmetrical curve centered around the mean, spoiler alert, later on we're going to call this kind of distribution a normal distribution. So as long as your distribution is a bell-shaped symmetrical curve centered around the mean, we expect about 68% of the values to fall within 1 standard deviation of the mean. So z-scores between -1 and 1. For this kind of distribution, we would expect to see about 68% of the values in here. By the way, I should mention this. I don't know if we've ever looked at this kind of curve before. This kind of curve is what would sort of fit over your histogram, all right? So imagine a histogram where the bars are pretty low out here, and they get higher as you get closer to the mean. So if you can kind of fit this sort of curve over that histogram, then that's the kind of distribution that we're talking about, okay? So about 68% of the values within 1 standard deviation, you would expect to find about 95% of values to fall within 2 standard deviations of the mean. So z-score is between -2 and 2. And then finally, you would expect to find about 99.7% of values to fall within 3 standard deviations of the mean. Z-score is between -3 and 3. So a moment ago, we said anything with a z-score bigger than +3 or less than -3, we call that an outlier. You would only, well, at least if the distribution looks like this, you would only expect to find values like that 0.3% of the time. So that's 3 times out of every 1,000. So not very often. Now, Chezevs theorem is kind of similar. One difference is that this works for any distribution. Any distribution does not have to be symmetrical, bell-shaped. So what this theorem says is that for any number z greater than 1, the percentage of values that fall within z standard deviations above and below the mean will be at least this percentage. Okay, now that's a lot to take in and kind of hard to understand until you see some examples. So for example, if I plug z equals 2 in there, let's try to do this in our heads. I don't think it'll be too hard. If I replace z with 2, 2 squared is 4, 1 over 4 is 1/4, 1 minus 1/4 is 3/4. 3/4 as a percentage is 75%. So this says that when z equals 2, at least 75% of the data values will fall within 2 standard deviations of the mean. Now compare that with what the empirical rule said. The empirical rule said that if your distribution happens to be bell-shaped symmetrical, then that percentage should be around 95%. All right, so the reason it's so different is because, remember, for Chezevs theorem, I have no idea what the shape of the distribution is. All right, so to kind of, put these two together, it's saying for any distribution, you're going to find at least 75% of the data within 2 standard deviations. And if your distribution happens to have this nice symmetric bell shape, then that number is actually around 95%. When z equals 3, let's go back to the formula. 3 squared is 9. 1 over 9 is 1/9. 1 minus 1/9 is 8/9. 8/9 as a percentage is about 89%. So when z equals 3, at least 89% of the data falls within 3 standard deviations. Empirical rule says that if your distribution happens to be symmetric bell-shaped, that number is around 99.7%. So it's at least 89%. And if you know it's symmetric bell-shaped, then it's actually around 99.7%. And then finally, when z equals 4, empirical rule didn't say anything about z equals 4. But for any distribution whatsoever, at least 94% of your data values will fall within 4 standard deviations of the mean. All right, and the last thing we have to look at in this section, I don't want you to think that this is just a completely different out of nowhere formula. If you take these formulas and you solve them for x, then what you get are these formulas right here. So these are very handy when you know the z-score and you're trying to find out what original data value does it correspond with, okay? So for example, if you have a symmetric bell-shaped population with a mean of 20 and a standard deviation of 3, what interval will contain about 95% of all values, right? So the reason they're telling me it's symmetric and bell-shaped, they want me to use the empirical rule. The empirical rule that says that about 95% of values are within 2 standard deviations of the mean. So to get the upper limit on this interval, I'm going to put in z equals 2. And so that's what we've done here. X is equal to mu plus z times sigma. The mean is 20. The z-score is positive 2. And the standard deviation is 3. So the upper bound of that interval will be 26. The lower bound of that interval will be when z is negative 2, 2 standard deviations below the mean. So that's going to look like this. I'm not crazy about the way they wrote this. I would have written it like this. I hope this doesn't confuse you, but it almost looks like they're using a different formula. So I would have made this a plus, and I would have made this a plus, and I would have put my negative sign here. That makes more sense to me. Okay. And my negative sign doesn't look like a negative sign, so let me try to fix that. There we go. Okay, good enough. All right, so 2 standard deviations below the mean would be 20 plus negative 2 times 3, which comes out to 14. So in this scenario where the mean is 20 and the standard deviation is 3, if your distribution is symmetric and bell-shaped, you will find about 95% of the values will fall between 14 and 26. And that is going to do it for section 3.3. We'll see you next time.